What specific problem does your proposed method of replacing the softmax attention mechanism with the sigmoid function aim to address? Can you elaborate on the limitations of softmax that motivated this change?
The proposed method of replacing the softmax attention mechanism with the sigmoid function aims to address the limitations of softmax, particularly its tendency to concentrate attention on a few features while neglecting other informative aspects of the input data. This concentration can lead to suboptimal token representations, as softmax requires a row-wise reduction that can slow down computations, especially in efficient attention kernels. By substituting the row-wise softmax operation with an element-wise sigmoid nonlinearity, we alleviate the issue of large initial attention norms that can hinder performance. Additionally, the sigmoid function allows for a more flexible and efficient computation, as it does not require the same normalization process as softmax, thus improving both training and inference speed. Overall, this change enhances the model's ability to capture a broader range of features in the input data while maintaining computational efficiency.
Can you explain how the proposed sigmoid attention mechanism works? Please illustrate it step by step, including the role of the learnable weight matrices and the activation function in the process.
The proposed sigmoid attention mechanism, denoted as 19, operates by first defining an input sequence composed of vectors, which are processed using three learnable weight matrices to compute queries, keys, and values. Specifically, the input sequence is transformed through these matrices to generate the respective representations. Instead of the traditional softmax normalization, the mechanism employs an element-wise sigmoid activation function, which is applied to the input matrix, allowing for a more flexible and efficient computation of attention weights. This sigmoid function includes a hyperparameter that can be tuned to optimize performance. The output of the sigmoid attention is then computed by combining the transformed queries, keys, and values, enabling the model to capture contextual relationships within the input sequence while maintaining the ability to approximate any continuous sequence-to-sequence function, as demonstrated in the theoretical analysis.
Could you provide a simple illustrative example that shows how your proposed algorithm processes an input sequence step by step? Walk us through the attention computation using your sigmoid attention mechanism.
To illustrate the processing of an input sequence using the proposed sigmoid attention mechanism, denoted as 19, consider an input sequence composed of three vectors, each of dimension 25. First, we compute the queries, keys, and values using three learnable weight matrices. Instead of applying the traditional softmax normalization, we utilize an element-wise sigmoid function, which is applied to the input matrix to generate attention weights. This sigmoid activation allows for a more distributed attention across all features, mitigating the concentration issues seen with softmax. Finally, the output sequence is computed as a weighted sum of the values, where the weights are derived from the sigmoid attention scores, enabling the model to capture global context while maintaining efficiency in computation.
What are the theoretical benefits of using sigmoid attention compared to traditional softmax attention? Could you elaborate on how you demonstrated that the sigmoid attention mechanism is a universal function approximator?
The theoretical benefits of using sigmoid attention, 19, over traditional softmax attention, 20, include improved regularity and a lower local Lipschitz constant, which enhances the robustness and optimization ease of the network. Specifically, the Lipschitz constant of 19 is bounded by the average squared norm of the input sequence, contrasting with the worst-case bounds of softmax, which can lead to higher sensitivity in certain scenarios. We demonstrated that sigmoid attention is a universal function approximator by proving that a transformer architecture utilizing 19 can approximate continuous permutation equivariant functions to arbitrary precision, maintaining the universal approximation property, UAP. This was achieved by showing that for any continuous function and small error, there exists a transformer network composed of multiple 19 layers that can achieve the desired approximation. The proof followed a similar path to that of classical transformers, ensuring that the modification to the attention mechanism does not compromise the representation capability of the architecture.
How did you validate the effectiveness of the sigmoid attention method? Describe the experimental design, datasets used, and the benchmarks or metrics for performance assessment. What results did you observe?
To validate the effectiveness of the sigmoid attention method, number 19, we conducted experiments across several domains, including supervised image classification using vision transformers, self-supervised image representation learning with methods like SIM-CLR and BIAL, automatic speech recognition, ASR, and auto-regressive language modeling, LM. We specifically evaluated the performance of number 19 against the classical softmax attention, number 20, on datasets such as TED-LIAM v3 for ASR and various image datasets for vision tasks. The performance assessment was based on metrics like negative log likelihood and accuracy, comparing the results of number 19 to those of number 20. Our findings indicated that number 19 matched the performance of number 20 across all tasks, while also providing significant speed-ups in training and inference, with improvements of up to 53% in realistic end-to-end setups. This comprehensive evaluation demonstrated that number 19 is not only effective, but also efficient in various machine learning applications.
What limitations or potential drawbacks do you acknowledge with your proposed approach? How might these limitations affect its applicability in real-world scenarios?
One limitation acknowledged in our proposed approach, specifically the use of sigmoid attention, number 19, is its sensitivity to the initial attention norms, which can lead to underperformance compared to the classical softmax attention, number 20, in certain scenarios. This sensitivity necessitates careful modulation through techniques like relative positional embeddings, e.g., alibi, or appropriate initialization of the bias term, number 56, to mitigate high initial attention norms. Additionally, while our method shows improvements in training and inference speed, it may still be slower than softmax in theoretical terms, which could limit its efficiency in highly demanding applications. Furthermore, the performance of number 19 in language modeling tasks remains largely unaffected by layer scale, indicating that its benefits may not be universally applicable across all domains. These factors could restrict the generalizability and effectiveness of our approach in real-world scenarios, particularly in tasks where initial conditions significantly influence model performance.